Good morning. Our lecture today is a continuance of Chapter 9, Rotational Motion. In this lecture, we will define moment of inertia and equations associated with various rigid bodies, and will perform example problems demonstrating how this concept would be used in the work setting. We are looking at objective number 2 for this chapter, which is to be able to state the definition of moment of inertia and use this to solve rotational dynamics problems. In a system of discrete particles, the moment of inertia, represented by uppercase I, is obtained by multiplying the mass of each particle by the square of its distance perpendicular from the axis of rotation and adding these products. Rotational inertia has the dimensions of mass length squared and is usually expressed in kilogram meter squared or slug foot squared. A slug is a unit of measure used when mass is described in pounds rather than kilogram. Our problems will typically use the SI unit of kilograms for mass. The moment of inertia of a body is a measure of the rotational inertia of the body and is analogous to mass in translational motion. Since moment of inertia plays the same role in rotational motion as mass plays in translational motion or linear motion. Although the mass of a body does not depend on its location, the rotational inertia of a body does depend on the axis about which it is rotating, as well as on the shape of the body and on how its mass is distributed. This lecture focuses on an axis of rotation which is fixed in an inertial reference frame. We will later examine situations in which the axis of rotation moves. Let's look at moment of inertia for a system which consists of one particle on a string moving in a circle counterclockwise about the axis of rotation. The axis of rotation is at the center of the circle and is normal to the plane of the circle. In this example, the mass of the particle is m and the particle is a distance r from the axis of rotation. The moment of inertia for this one particle is therefore defined as I is equal to mr squared. Let's look at a second system, which consists of two spherical masses, M1 and M2, connected by a light rod. This body is called a dumbbell or barbell. The axis of rotation is normal to the center of the system, and the system is rotating counterclockwise. M1 is a distance R1 from the axis of rotation, and M2 is a distance R2 from the axis of rotation. For this system, the moment of inertia would be I is equal to M1 R1 squared plus M2 R2 squared. The role of moment of inertia for rotational motions is similar to that of the mass when dealing with linear motion. This implies that the greater the moment of inertia, the harder it is to start the body rotating from rest or slowing it down when already rotating. How do we increase or decrease moment of inertia? In looking at the expression for moment of inertia, you would likely guess by either changing mass or by changing the distance from the axis of rotation, and you would be correct. On this slide, we have two systems in which an apparatus is free to rotate around the vertical axis. The masses are equal, so M1 of system 1 is equal to M1 of system 2, and likewise M2 of system 1 is equal to M2 of system 2. In the system on the left, two masses are locked close to the center of the horizontal shaft, which is the axis of rotation. On the right, the two masses are locked far from the center of the horizontal shaft or the axis of rotation. Which system will have the greater moment of inertia? So if we look at the definition or expression for system one moment of inertia would be defined as m1 r1 squared plus m2 r2 squared. If we look at system 2's moment of inertia would also be described as m1 r1 squared plus m2 r2 squared. So they have the same expression for moment of inertia, but the values that you put in for mass would be the same, but for the distance r1 and r2, the left system would have smaller r values and the right system would have larger r values. Because moment of inertia is dependent upon perpendicular distance of the mass from the rotation of axis, the value for moment of inertia would be greater for the configuration on the right. Therefore, we can decrease the moment of inertia by moving the mass closer to the axis of rotation or increase the moment of inertia by moving the particle further from the axis of rotation. Note that the apparatus on the right is also harder to start to rotate, since moment of inertia is a measure of the resistance a body offers to a change in its rotational motion about a given axis. This means that it will require more work or energy to start the system or slow the system. I found the following information on the web regarding birds' wings and thought it interesting for this particular topic. When a bird flaps its wings, it rotates the wings up and down around the shoulder. A hummingbird has small wings with a small moment of inertia, so it can move its wings rapidly up to 70 beats per second. In contrast, larger birds like a condor or eagle or vulture, turkey vulture, with larger wings have a large moment of inertia. Therefore, it moves its wings at a slower rate, and this particular bird is on average 1 beat per second. Up to this point, we have talked about systems with discrete particles. We don't always have nice particles to work with. Sometimes we have a complicated blob, like what you see here. The equation that I have given for moment of inertia is only useful for cases where the rigid body is made of a discrete arrangement of particles. For a complicated body, we imagine the body to be subdivided into infinitesimal elements, each of mass dm, and r is the perpendicular distance from each element to the axis of rotation. The summation expression then becomes an integral expression where the integral is taken over the whole body of the, quote, blob. The moment of inertia can also be found by integrating over the volume of the mass, where rho is the mass density of the body. And since we're working with rigid bodies, the density would be constant. And dV is the elemental volume where dm is located. For bodies of irregular shape, the integrals may be hard to evaluate. Our text gives us a table with the moments of inertia for some common solids, which we will be using in problems. You are not expected to memorize these. You will notice the expressions for moment of inertia contain capital letters. For instance, mass is a capital M rather than a lowercase m. Length is a capital L or capital R. For whole systems, capital letters are used to represent the entire system. So capital M is the mass of the entire system, whereas lowercase m was the mass of a particle. Note that the position of the axes about which the moment of inertia is calculated, the axes of rotation, will affect the value of the integral. Let's take a closer look. Here we are looking at rods and rectangular plates. you will notice that the moment of inertia for the slender rod where the axis is through the center is less than the moment of inertia for the rod where the axis is through one end. Why? If you look at this, the percentage of mass for this rod where the axis is through the center is closer to the axis of rotation than this rod. This rod has at least 50% located further from the axis of rotation. You will notice this is also true for the rectangular plate. And the rectangular plate that has the axis of rotation through the center also is dependent upon the length of the plate, whereas when the axis of rotation is at the end of the plate, it's only dependent on the width of the plate. Let's look at cylinders. Let's start with the hollow cylinder. The thickness of the hollow cylinder is very small in comparison. Didn't mean to do that. To the radius or the distance from the axis of rotation. So we will assume that each particle in the hollow cylinder is a distance r from the axis of rotation. Again, the solid cylinder, and I am going to call both of these solid cylinders, since this equation or this expression is the same, but R1 is equal to 0. But the solid cylinder has a smaller moment of inertia than the hollow cylinder. Again, why? Because the percentage of mass located near the axis of rotation is closer to the axis of rotation than for the hollow cylinder. Okay, and as I popped up here, the moments of inertia for cylinders does not depend on the length of the cylinder like it does for a rod. And cylinders are very similar to rods. However, the axis of rotation runs along the length of the cylinder versus being normal to the cylinder like a rod. Since the moment of inertia doesn't depend on the length of the cylinder, we can say the moment of inertia for a disc is the same as the moment of inertia for a solid cylinder. And the moment of inertia for a ring is the same as the moment of inertia for a thin hollow cylinder. So this will be useful to know when we are working on homework problems. Lastly, moments of inertia for spheres. Like the hollow cylinder, the thickness of the hollow sphere is very small in comparison to the radius of the sphere. Therefore, we can assume that every piece of the hollow sphere is a distance r from the axis of rotation. And again, the solid sphere has a smaller moment of inertia than the hollow sphere because a higher proportion of the mass is located closer to the axis of rotation. Let's take a look at an example problem. We have a flywheel, or a wagon wheel, excuse me. And I am going to share my tablet so that I can work on the problem here. And it will pop up. Okay, there we go. Okay. The wagon wheel is shown in the figure. The radius of the wagon wheel is R is equal to 0.300 meter. The mass of a spoke is 0.280 kilogram, and the mass of the rim is 1.40 kilogram. What is the moment of inertia of the wheel? About the axis of rotation, which is through the center and perpendicular to the plane of the wheel. So our axis of rotation is right here in the center, and it's coming out or poking in to the page or the plane of the wheel. Now you may be wondering, why do I care about a wagon wheel? We all have to start somewhere, and this is a foundational place to start. And we still have flywheels in engines and various contraptions. And so, okay. The moment of inertia for the wheel is equal to the parts that make up the wheel. So we have the rim, so we have the moment of inertia for the rim, and we have 8 spokes. So the rim has a moment of inertia that is like a ring. And we had said a ring had the same moment of inertia as a thin, hollow sphere. And the moment of inertia for a thin, hollow sphere is mr squared. And we got that from table 9.2 in our text. All right, now let's look at the spoke. A spoke looks very much like a rod. However, which rod? Is it the rod that has the axis at the end or at the center? And our axis of rotation is at the end of the rod. So the expression for that type of rod is 1/3 m length squared. And we have 8 spokes, so it'll be 8/3 L squared. Okay. So let's go back to our expression for the wheel. So the wheel is the moment of inertia for the rim, and that's mr squared. So our mass of the rim is 1.40 kilogram, and the radius of the rim, or the distance of the rim from the axis of rotation, was 0.300 meter, and that's squared. And then we have 8 spokes, and each spoke has a mass of 0.280 kilograms. And each spoke had a length of 0.300 meter, and that is squared. So our wheel has a moment of inertia of 0.126 kilogram meter squared plus 0.0672 kilogram meter squared, which gives us a total of 0.193 kilogram meter squared. And that would be our answer for this problem. Okay, let's go back to our PowerPoint here. And we just did this problem. Now let's move on. We defined moment of inertia and the various formulae used to calculate it for both discrete and continuous bodies. We reviewed table 9.2 and discussed why similar bodies have different moments of inertia expressions. And lastly, we performed some example problems. We can now add moment of inertia to our list of angular quantities that are analogous with linear motion quantities. And we will discuss rotation about a moving axis, kinetic energy, force, and momentum for rotational dynamic systems in the next lecture. And that concludes this lecture.